the organizers this morning, so I'm afraid the copies aren't out there yet. But rest assured that they'll be on the web, and if you like to take notes now, then you can cross-reference them with the plots that you'll see here in the slides. So by now in these experimental lectures, we've heard about the LHC machine, the Large Hadron Collider Accelerator, and we heard about the physics of the particle interactions with the detector. We talked a little bit about the jet physics, and for today's lecture, I'll be talking about something that you heard already from Matt on the theory side about the Higgs mechanism. And basically, these lectures are going to focus on a specific search for a new kind of physics or a new particle, the Higgs boson. It'll be the standard model Higgs boson that I'll focus on exclusively today. And tomorrow we'll hear from both the theory side and the experimental side about non-standard model Higgs bosons and other new particle searches. Okay. So I've picked the Higgs boson today because, number one, it's something that's still standard model. I guess maybe people could debate whether Higgs is really standard model or not. For me, it's kind of standard model because it's the explanation for W and Z masses. This model is a very specific model. So what it means is that we know exactly what the couplings are for Higgs. We know how it couples to all the standard model particles. We can calculate its properties, even at next to next deleting order, its decay rates and its production rates of the LHC. This is different from what we'll be talking about tomorrow, where we'll be talking about a more general search. In other words, casting the net very wide to anything that might be out there without prejudice of a model. In this case, we might be able to get away with a prejudice of a certain model, which is the standard model. So that's the approach we'll take today. So let me start by saying what's known. I just claimed that we knew a lot about the standard model Higgs boson already, that we knew a lot about the couplings to the various standard model particles. In fact, we saw that during Matt's lectures, Matt's theory lectures. So knowing these couplings, we can do calculations of all of the corrections that the particles in loops could have to W and Z masses. In fact, let me say a little bit more about that. I can't remember if Matt showed this or not, but if we look, for example, at some of the boson masses, let's take the W mass, for example. You know that in the W mass, you have both the bare W, and you have these loop corrections. Oh, I remember I'm supposed to push harder with the chalk, so let me try to push harder. Okay. So we have loop corrections that include both fermionic loop corrections. So you could have something that's a W here, and then it would have CKM partners, the T and the B. So that could be a correction to the W mass. You could also have, through the HWW coupling that Matt mentioned, you could have a correction to the W mass that involves, I guess I should draw this as the scalar, that involves the Higgs and the W. Okay. So we can actually see the effects of the Higgs, if it exists, in the W mass, just as we could see the effects of the top on the W mass through this loop here. So in fact, if you go ahead and do the calculations here, you'll see that the corrections to the W mass, the corrections that are due to the top quark mass come in quadratically. So the W mass measurement is a very tight constraint on the top quark mass. And in fact, the top quark mass was first predicted long before it was discovered, around 175, 78 GeV. And we know today that from direct measurements, it's about 173 GeV, so that was spot on. Unfortunately, the contribution from the Higgs boson loop is only logarithmic. And so the correction to the W mass is logarithmic in the Higgs mass. So that means that we have a much weaker constraint on the Higgs mass. And this is reflected in the plot up above. If you look at the measurements that we have for the W mass on the vertical axis and the top mass on the horizontal axis, you can see that the two of these combined give a constraint on the Higgs mass, which is kind of the vertical bands that are going up. I hope everyone can see that. So this is one way of plotting the famous blue band plot with a global minimum for the Higgs mass that some of you might have seen before. But this shows directly that some of the largest constraints are due to the direct measurements there of the top mass and the W mass without anything else. So from reading off of this plot, you could see that the center of this ellipse which is the precision measurements of the top mass and the W mass, would predict a Higgs mass that is actually much lower than 114 GeV. The problem is that we've already searched for the Higgs boson at the LEP collider and already ruled out all the Higgs boson masses below 114 GeV. So there's a little bit of, tiny bit of tension there between experiment and theory. I say tiny bit because the ellipse there is the 68% confidence level, or what we might typically think of as 1 sigma. I'll say a little bit more about that. But you can see that that 1 sigma ellipse even touches the area that we haven't seen yet. So it's not a strong tension between the theory and experiment. It is telling us in some way that the Higgs, a heavy Higgs, would not match up with this idea of the corrections, would not match up with the electroweak corrections as we've calculated them. In other words, a Higgs of 1 TeV would not fit in with these electroweak measurements that we've made. Two other things you can see. The LEP searches rule out 114 GeV. That's why you have the purple line there on the top of the graph. And then you see another line here, this white line, that is another excluded region in the middle of the green space. And that's the excluded region from the Tevatron. So Tevatron, after, let's see, how many years? After 7, 8 years of running at 1.96 TeV, has ruled out a small slice of the possible Higgs boson masses. Okay, that's the first Higgs boson exclusion in 7 years since the LEP machine turned off. Okay, that's exciting. So this is what we know today. The reason I put this up right away is what I'll be showing for the rest of the time is basically concentrating on the slice of Higgs boson parameter space, the mass parameter space, between 100 GeV, actually let's say 110 GeV since it's already excluded below 114. So 110 up to 200. And I think you can see from the ellipse there that we have some pretty good indications that the Higgs, if it exists, will likely be found in that mass range. I'll say a little bit more today and a little bit tomorrow on what happens if the Higgs is much heavier than that. Okay. All right. These are the Higgs production mechanisms. In order to search for the Higgs at the LHC, we have to first produce it. So Matt mentioned already the main production mechanism, because we have a hadron collider, is due to the gluons. So we have the gluons. He mentioned that the gluons don't couple to Higgs because the Higgs is coupling to mass. So the only mechanism for producing the Higgs is through one of these fermion loops. So it has to be a fermion loop. Usually it's the top quark that dominates in these kinds of loops due to the mass. So this is the main production mechanism, often called, let me write it here, gluon fusion. Okay. So we'll see that there are some channels in which we can see the Higgs through gluon fusion, other channels not. Some of the other channels up there, you see that there's a QQ bar to WH. So QQ bar to WH. Let me see if I can do this off the top of my head here. So we have Q bar can go through either a, well, let's do the Z first, huh? So we could have a Z here. Actually, it should be a Z star. And then the Z, because it's coupling to the Higgs, can radiate a Higgs. So you have what some people would call the Higgs-Strahlung HZ production. So you can think about this as being, instead of a photon radiated, the Higgs scalar being radiated, Higgs-Strahlung. So this would produce the HZ signature, or if you replace this with a W, if these are Q and Q bar prime, you would get a Z instead, or sorry, a W instead, so you'd have WH. And what am I missing up here? So QQ to QQH is another one, and that basically looks something like this. So if we start with a Q here, we can have, among other things, a internal bosons like this. So maybe these are W's. And then those W's are merging or fusing to give us a Higgs. So this is called the vector boson fusion, or some people call it weak boson fusion, but vector boson fusion seems to be taking the lead in the nomenclature these days. Okay. So these are the three main production mechanisms that I'm going to talk about today. There's also a production mechanism where the Higgs is produced in association with TT bar. By the way, what happens here in vector boson fusion, these are the quarks, right? So this is that QQH final state up there. Okay. You also get an idea from this plot about what the relative production rates are. Again, at 14 TeV, you can see that if you think about low mass Higgs, which is I'll define as being around 120 GeV, you can see that the total cross-section dominated by the gluon fusion is about 30 picobarns, I think is what I quoted in the last set of slides. And the others are far below that, maybe 1 order of magnitude or 1.5 orders of magnitude below that. Okay, that'll be important whenever we consider the event rates that we'll get in the data. There's a question, yes?
So, experimentally, do you expect to find the Higgs, say, on shell, or do you expect it to decay to something else and then measure what it decays to?
Right. The question was, do you expect the Higgs to be produced on shell, produced and decay on shell, right? So the answer to that is yes, that we are expecting it to be produced on shell and then to use the decay products to take the invariant mass and find directly the Higgs mass. In other words, reconstruct directly the Higgs. Basically in the same way that we would do that for a Z boson, right? You could ask the same question about a Z boson, right? So it's exactly the same idea. In fact, it's so much the same idea that in several of the search techniques that I'll show you today, we can use the Z as a test, as a proxy, a standard model proxy for what we expect to happen with the Z boson.
How do we know that product it came from Higgs? Are we going to go through the list of the particles that we know and see, okay, it's not the Z, it's not the W, it's not this, it's not that?
That's a great question. Okay. So just to skip ahead a little bit, if you discover something where you have, let's say, two Z's that are being produced, and they make an invariant mass peak, then you'll know that something was produced that decayed to two Z's and had a very specific mass. So you could say it's the Higgs. You could say it's something else that maybe we don't know about. And so what I won't talk about today is how we know for sure that it's the standard model Higgs. That's a very good question, because we'll talk in the theory next time and on the experiment next time about other Higgses that could be produced. And in fact, there's a great deal of effort that people are going through trying to define how we will know once we discover something what exactly it is. Is it a standard model Higgs? Is it a Higgs from another model? What exactly? So that's a very good question. We're happy to find something first, okay? But it's good that you're thinking ahead. That's very good. These are the branching fractions then. I mentioned, for example, that the Higgs couples to ZZ, for example. In general, the way that this works is we know exactly what the couplings are. We can calculate exactly what the width is for any sort of Higgs to fermions, for example, or Higgs to WW or ZZ, okay? We can calculate those partial widths exactly. What makes it interesting is to calculate the branching fraction. As the fraction of the time the Higgs will decay to each one of these signatures. We have to divide each one of those partial widths by the total width. So the total width is changing as a function of the Higgs mass. The Higgs mass is the only free parameter here. So what changes as a function of the Higgs mass are not the partial widths change, but then really what we're looking for are the branching ratios that change. So this can be calculated exactly. Let me say a few words about the different ranges here. So first of all, let's take something that's an easy range to think of. Why isn't TT bar on there? Is that the question? Yes. That's a good question. Okay, so first let's think about what happens when we have a Higgs mass that is above, let's say, 2mz. Okay. It turns out that, so if it's above 2mz or even above 2m top, even though we say that the Higgs couples to mass and the top quark is more massive than the Z, you might expect it to couple more strongly to the Higgs. But now think back to what Matt said about in his lectures, right? He was talking about not only does the Higgs couple to mass, but there's this extra secret enhancement, not secret, but we don't usually think about it, which is the Higgs is coupling specifically to those longitudinal degrees of polarization. I have this right? Basically what he said. So he was talking about it in the context of W's, if I remember right, but the same thing happens for Z's. So these gauge boson couplings to the Higgs are enhanced because, after all, the Higgs is related intimately with those degrees of polarization. So, okay. So that explains why it's not necessarily top. So if the Higgs is above 2 mz, you might say, well, it will couple to mz. It actually turns out, if you look at the plot here, the z line is below the w line. So here's the z line, and the w line is up here. And the reason for that is because of this Lagrangian term here. So you actually have a factor of 2 difference in the coupling, assuming that mw and mz are close together, between the coupling to the w's and the coupling to the z's. So when you square this, you get a factor of 4, but then since you have symmetric particles here for the z's, you take away another factor of 2. Basically, at very high masses, the w branching ratio will be about twice the z branching ratio. You can't quite see it on here because we're not quite high enough to be much, much higher than mz. Okay. So if mh is above 2 mz, we have the dominant decays being the ww decay and the zz decay. As we go below 2 mz, then you'll expect the coupling or the branching ratio to the z pairs to turn off, and that's exactly what happens there. So you can see it go down. So if mh is roughly between 2 mw and 2 mz, actually let me say it a different way. Let me say that that's fine. Okay. So in that case, we have the decay to w's almost exclusively, and that's the point where the w branching ratio gets very large up there. If you go a little bit lower than that, actually let's just skip back down to what happens when we're below mw. So if I have the Higgs mass significantly below twice mw, I'm far enough off shell that I can't produce 2 w's, so that decay will be closed out to me. So what's left? Now I've closed off all the couplings to the gauge bosons, except the photon, which we'll come to in a second. So what's left are the fermions. So we already said that the top quark would be the strongest coupling because of the Yukawa coupling. But actually, we're closed off there too for the phase space. So the next one would be B's. So in fact, the dominant decay there is BB bar. And also a little bit of tau plus, tau minus, you can see. Right? Okay. Now, let me say one thing about this little bit down here that we have for the photons. So you've all heard about Higgs to gamma gamma, but the Higgs doesn't have any direct couplings to the gamma, so how does that work? Well, you saw, I think, that through the same sort of fermion loop that you had the connection to the gluons, you can also have the connection to the photons. Okay. So this is obviously suppressed because you have these factors of alpha in here in the loop. And so this branching ratio is far reduced, I mean, order of 1,000 down from BB bar. Nevertheless, because it's such a clean detector signature, we'll see in just a minute that this is one of the preferred Higgs searches. So let me just add it down here. It's not necessarily the third largest, it's just the one that we will use for this range. Okay. Are there any questions about this so far? What I'm going to propose to do is go through and talk about how we will actually do the searches in each one of these ranges. Question?
So what's that big drop in the Z? Is that just a mass threshold?
So at that point, so the reason that there's a dip is before you get up near 160, you can't produce the W's on shell. So basically the total width of the Higgs is small. Okay? So the partial width of the Z might indeed go like this. But what's happening is the total width goes like this. It follows along here, and then it jumps up when you get to the W mass. Okay? So that Z dip, you can see, corresponds exactly with the point where the W partial width, WW partial width, becomes very large. And that's why the fraction goes down. Okay? As the Z continues to increase, then it starts to build back up. Well, actually, as you get to 2mz, and you can make on-shell Z's, that's when it climbs back up, see, at 180. Okay? So it's a combination. This is the key, is to look not only at the partial width, but the branching ratio between the partial width and the total width. It's the total width that can be changing in an interesting way because it has many contributions. Oh, there's a question over here too. Question? No? Okay. Yes?
What it is that the platform has already ruled out the small radar incidence. Why is that special? It's just a 160 ring.
Right, so I could ask you, what is special about 160? What's the most promising channel there? You can read it off the plot and behind me. W's, right? It's no coincidence that the place that is ruled out is the place where you have that maximum WW production, 163, just above MW to MW.
But why does it stop at 166?
Why does it stop at 166? So the reason is, if we go back to the production cross-section here, this is the cross-section for LHC, but it's also true for Tevatron. It's basically a falling cross-section, okay? So there are two reasons that it might stop at 166. And I can't tell you the answer off the top of my head, actually, but the one reason could be the cross-section, the production rate, falls so that you don't produce enough Higgses anymore to actually be able to exclude it. I mean, think about it this way. If you produce 0 Higgs, if you expect to produce 0 Higgs, and you see 0, then you haven't excluded it, okay? So what happened, that's why you have some upper limit on your reach. The other reason could be that there might be some candidates that look like Higgs, and therefore they weren't able to rule out Higgs. Okay, so we don't know that without having seen the result. But those are the two reasons that it might be. Okay, any other questions? Yes?
Is it possible the Higgs to break into leptons? Or is it going to be very light in that case?
So the question was, can the Higgs couple to 2 leptons? Absolutely, it couples to 2 leptons, but the coupling is very small because of the fermion mass. Okay, so basically is fermion mass squared. Do I have it right? Fermion mass squared. Taus are up there. Great point. So those of you who remember standard model, taus are heavy. So taus are as heavy as charm. Okay, so you can see that even though charm and tau have exactly the same mass, there's a little bit of difference in their partial width, and that does come back to the difference between the leptons and the quarks. Okay. So let me say a few words about the general overview. So we just had a brief question about how we exclude or where the exclusion might leave off at some point. Let me do some explaining about that. So the basic idea behind all these searches, the ones that I'll talk about today, the ones I'll talk about tomorrow, we are choosing for the standard model Higgs search in a very specific way, a very specific model, and we know the signatures of that model. Now, the reason that this is very important is that we'll be looking to select a sample of events, and we'll be checking to see whether that sample of events is consistent with what we expect without Higgs production. So we have 2 possibilities. If we look for, let's say, the 2 Z bosons, we can either have the possibility that it matches what's expected from the signal plus the background rate. Okay, and the signal in this case is the standard model Higgs, and the background in this case is all other physics. So anything that's standard model, not Higgs. Okay. And what we'll want to do is we want to compare that to what we expect from background only. And the background only is, of course, the standard model, not Higgs. So the proof of our discovery would be to find something that is not compatible with background only and is perfectly compatible with signal plus background. Okay. The reason I stress this is a little bit different from what we'll be seeing tomorrow, where we might not have a well-defined model, and then we'll just be looking for a discrepancy from the background. But for the Higgs, we have this extra power that we know or believe we know the model exactly. We'll see how true that is. Okay. So there's a lot of work done, not only to develop the event selection, to select a certain signature, estimate what the contribution is from the background and from the signal, and then to calculate what the probability is that this is consistent with the Higgs.
When you say
Yes?
well-defined model, you mean that there's many candidate models, and so you just sort of look for differences from the background? Or?
That's what we'll be talking about tomorrow, so both on the theory side and experimental side. An example might be, we will look for a generic Z prime production, where Z prime is a heavy Z, without any bias about what model that might come from or at what rate it might be produced. Okay. And with Higgs, standard model Higgs is very special because we believe we know exactly the rate at which it's produced, even at next to leading order. All right, I'd like to say a few words about statistics. And the reason is that statistics is something that's very important to experimentalists, but the theory community doesn't often have to use statistics as much as the experimentalists, okay? Because you're not counting up events, right? Your duals and your ADS-CFT doesn't necessarily have statistical uncertainty. So I want to say a few words about that, so that next time you see a paper from Fermilab or from the LHC saying 3 sigma discovery, you'll know exactly how you feel about it. I hope you will, okay? I don't want to tell you how you feel about it, but you can discuss with your friends. So let's take a concrete example. Let's say that we expected to have 40 background standard model events, okay? So just to have a very simple example, maybe we do something like this. Maybe we say that we're looking for Higgs to ZZ. Okay. Let's say that I have 40 non-Higgs SMZZ. Right? We can produce 2 Z bosons without it having to come through a Higgs. Let's further say that we might expect that if the Higgs is produced, that there will be 10 such ZZ events produced through the Higgs. That's the signal that we will say. 40 would be the background, 10 would be the signal. So you might say, okay, the probability for us to find, let's say, 39 events when we expect 40, we should take the Poisson distribution, we should try to figure out what that probability is. We use the central limit theorem, though, to take advantage of the fact that our experiment is one of any number of possible experiments that we might see. So the central limit theorem is basically saying, if you did this measurement many times of many different experiments, what distribution would you have for the number of observed events? Of course, we're only going to get to do one experiment. All right? Our experiment will run for some number of years, and then we'll count up the number of events, and that will be the experiment. But we should always think of it in a statistical sense of having any number of outcomes. So the distribution of all the possible outcomes follows this Gaussian distribution according to the central limit theorem. You're not surprised to find that it's peaked at 40, and you're not surprised by looking at the RMS that it's approximately the square root of 40. Okay? So that's familiar to everybody with the Gaussian distribution, that the RMS, or the width of the Gaussian, if you want to think of it that way, is the square root of n, where n's the number expected. So the question for you would be, if I were standing up here as a speaker at a TASI and saying, we observed 50 events. 50 is 40 plus 10, right? So should you be excited? Is that a Higgs discovery? That's how many we expected for Higgs, right? Some people shake their head, no, why not? It could be. It could be. Why?
When you say 50 events, what does that mean?
So it means that this is the number expected. Let me be clear. Thank you. This is the number that we might expect according to our simulation, our efficiencies, our expectations for how many standard model events we would see. But the number that we would collect in the detector might be 50. 50 seen in the detector, in the experiment. Okay? So some people shook their head no. I think the reason they're shaking their heads no is because you can see there's some probability, not a small probability, to observe 50 events even if we expected 40. Okay? So there's some probability for that to happen even without the Higgs. So at that point you'd have to ask yourself, is it more likely that we discovered the Higgs, or is it more likely that there was a fluctuation of a little less than 2 sigma to 50 from 40? How can you possibly observe more?
No, why is bad?
Why is it?
Why is it bad?
It's not bad. I wouldn't say it's bad at all. No, it's not bad. In fact, there's neither bad nor good. Can I make a slogan, Nadi? I'll say there's neither bad nor good. It's just what you see in the experiment, right? I guess if you're hoping to discover Higgs, seeing 20 would be bad, because then you're pretty sure that it's not. Okay, but 50 is neither bad nor good. You don't have any idea. you don't have any absolute idea whether it's due to the extra 10 events from Higgs production or whether it's just a fluctuation of the background. So there's quite a bit of work that goes into calculating what is the probability that this observation of 50 events is due to 40 plus 10 versus 50 as a fluctuation. There's a question up there.
So I can't resist asking this. So I guess there was some Higgs seen in the last 6 months of LEP. Where on that graph is that?
Good. I'm glad you asked that. Actually, we're going to come to that in just a second, okay? The probability. Shall we do that? Okay. So if you see 50, if you see 60, then you start to get a little more interested because you say, aha, 60. Well, it's very unlikely that that would be due to the background only, but that could be due to 50 plus the 10 Higgs that I expected, so maybe it is Higgs after all. Okay, let's be quantitative about that. So this is coming back to your question there. So you might have heard people talk about so many sigma. What does it mean, so many sigma? It's very easy to talk about sigma whenever I say that my height is, let me make up some number here, 1.9 plus or minus 0.1 meters, okay? So it's very easy to talk about what the sigma is here. That's the uncertainty on the measurement. It means that if I did a whole bunch of measurements, I would have a distribution of measurements centered at 1.9 with the width of 0.1, okay? But if you talk about probability, like what's the probability that the Higgs was observed at LEP2? We talk about that in terms of sigma, but it's actually just a probability. So here's the lookup table between probability and the sigma. Okay? It just comes from integrating the tails of a Gaussian. Basically what we do is we redefine all these probabilities as being the tails of the Gaussian. Okay? That's just that actually has some mathematical power. We'll see whenever we do a likelihood. But it's also useful because it's just a shorthand. People can get an idea about what 2 sigma means, 3 sigma means. Okay? I was thinking it could have been the football odds too. You could have said that something that's relatively likely to happen would be something like Spain winning World Cup. And something very unlikely to happen would be Australia winning World Cup. Okay? I actually was thinking about trying to convert the probabilities into those odds. Right? That's why I was on Paddy Power last night, not for any nefarious reasons. Okay. So sigma is the shorthand here. Someone asked what happened at LEP. At LEP, at one point, there was the claim of a 3 sigma probability. So that 3 sigma corresponds to about 3 in 1,000 probability. Okay, when everything was combined together, then that went back down to something like a 2.5 sigma or 2.2 sigma probability. So you could look up in there what the 2.2 sigma would be. Okay. So recently we had some indications from or we had some papers published from Fermilab talking about 3 sigma again. So now you have a good idea for figuring out just what those probabilities mean exactly. So when we're talking about vocabulary, one of the things we do at schools like this is to make sure that we're all speaking the same language and using the same vocabulary. You have to ask your experimental colleagues whether they're talking about a one-sided or a two-sided definition of alpha. And the reason is these are the translations between the two-sided definition, that is dividing equally the tail on the high side and the low side, and doing that, giving a probability for that number. If a person were to only use the high side instead, but somehow quote the double-sided, then they would be artificially inflating the number of sigma. So whenever you have a one-sided versus two-sided, it's just good to ask, okay? What would be much better is if they just told you the probability, I think, but you can't always count on that. Okay. Are there any other questions about this? I think that if you know the integrals of the Gaussians, then you know about these tails already. Let me say another word about that. So experimentalists distinguish between 2 different kinds of uncertainties. One is the statistical uncertainty and one's the systematic uncertainty. So my definition, quick definition of these two, is the statistical uncertainty is the uncertainty that you can expect to scale as you get more data. Okay. In other words, if I had if I made a whole bunch of measurements, let's say, so the uncertainty on the number of events divided by the number of events. Well, the uncertainty on the number of events was root n. And when this gets divided by n, I have 1 over root n for the relative statistical uncertainty, the relative uncertainty. So an uncertainty that will scale like this is what I would call a statistical uncertainty. You know that if the experiment gets 4 times the data, the statistical uncertainty will be halved. Okay? But that's by contrast with another kind of uncertainty that we call the systematic uncertainty. And the systematic uncertainty is really an uncertainty that's inherent in the method that's used. So an example of an uncertainty that's systematic would be if somehow you are using a certain method to tell you how many background events you expect. And if instead of 40, you're always consistently a little bit low and you have, well, let's say that you have an uncertainty, 35 plus or minus 5. Okay. Once this gets propagated through into our calculations for how likely you are to see a certain number of events, this is an example of a systematic uncertainty. Why is that? Because this plus or minus 5 comes from the method. Okay. So it's the method that gives you a systematic uncertainty because the uncertainty on that method won't change as you accumulate more data. Okay. So unfortunately, a lot of times we will be tricky and combine the two. So we might say something like 1.0 statistical uncertainty added together in quadrature with 1.0 systematic uncertainty, right? This is on some NN measurement. So altogether, that would give you a total uncertainty added in quadrature of 1.4 total. Okay, so you would have a quoted result that's NN plus or minus 1.4. It's much better if they're broken up like this because then you can see which one will scale and which one won't. And you can apply the scaling yourself, saying, aha, if this experiment were to have 4 times the data, this statistical uncertainty would decrease by a factor of 2, while the systematic uncertainty would remain the same. And then you can recalculate what the new uncertainty would be yourself. So it's important to keep those two separate. One of them will scale, one will not. Okay. Good. I'll say a few words about the likelihood techniques that are used. And part of the reason for that is whenever you read these papers, the real information about what the experiment saw is contained in that likelihood. It's not necessarily contained in the final number of sigma. Okay. Much more information is contained in the likelihood itself. I think maybe we can go quickly through this, but I hope everyone's familiar with the idea of the maximum likelihood. It's nothing more or less than a probability that you see some number of events n, up in the formula there, given some expected number of events s. Okay, so s is the number of signal, for example. B here would be the number of background. The expected number that you should see is s plus b, the expected number of signal plus the expected number of background. So this likelihood gives the probability to see any number in that range. If we go back to our 40 would be b, s would be 10, and n would be whatever the numbers were on the Gaussian that we had. Let me use this Gaussian here. So we'd have a Gaussian distribution. It would be centered at s plus b, you would expect it to be. And yeah, it would have that sort of, this would be the probability, or if you like, the likelihood. And this is n plotted here. N. Okay, so if you go through and you maximize minus log of the likelihood, actually maximize the likelihood, you'll get a maximum likelihood probability for S equals n minus b hat. So S hat and b hat are the expected. And you can see here that n, the maximum n, or I should say the maximum probability, p max, as a function of n, happens at n equals S hat plus b hat. Okay. So if you observe some value of n, and you're trying to figure out how many s's you have, the most likely value of s is whatever number you observed minus the number of background that you expected to get. Okay, let's go back and put those numbers in that we had before. So 40, 10, 50. What it's saying is that if I see 50 events, if I count 50 events and I expected 40 background, how many signal did I have? The most likely value of signal that I had was 10. But we said that the B could fluctuate from 40 up to 50. In that case, the S would be 0. We saw 50, but they were all due to background fluctuations. So the key for all these searches is trying to calculate what's the probability that we saw a signal. I mean, there's some probability that we had S equals 0 signal events, but there's also some probability that we had S equals 10. And the certainty with which we can exclude S equals 10 will tell us whether or not we're excluding the Higgs. The certainty with which we can exclude S equals 0 will tell us if we're discovering the Higgs. If we exclude S equals 0, that means we proved that S is not 0, that there really were Higgs signal events produced. That would be a discovery. Okay. I think that bin likelihood is the same idea, but just using information in the bins. Okay. And the likelihood can have an uncertainty itself. Basically, you have some sort of distribution of the likelihood. And if actually, let me skip this part. You can come back. It's enough to know that there is a way to calculate the sigma, again, a probability, by using the likelihood. Okay, good. This is the very last slide on statistics. Bear with me with one more slide. It's kind of what I just said in words just a few seconds ago. We're really trying to test two hypotheses. One hypothesis is that S equals 0. That is, there were no Higgs bosons produced. So in that case, any fluctuation that's seen away from the background expectation is just due to fluctuations in the background. And we can calculate the probability that that's what's happening in the experiment. The other hypothesis is that there's Higgs produced in addition to the background. Okay? And if that's the case, then that's basically the signal plus background hypothesis. That's what we would call the discovery hypothesis. So all these Higgs searches in the end, after all the event selection and background calculation, boil down to making a statement to you and to the community about which one of these hypotheses is favored and by how much. Okay. Or another way to say it is, what's the probability that this hypothesis could be true versus the other hypothesis? Okay. So that's what we should be doing. Someone mentioned 3 sigma. I think the standard of proof now in the community is 5 sigma. So people wouldn't get too excited about a 3 sigma anymore. There is one reason to get excited about a 3 sigma probability, though, that something new is happening. And the reason is that 3 sigma with 1 inverse femtobarn of data can turn into 4 sigma with more data, and then can turn into 5 sigma. Okay? You don't have 5 sigma spring up overnight. It has to start as 3 sigma at some point. Okay? So that's the reason that you can get a little bit excited about 3 sigma. Get very excited about 5 sigma. So 5 sigma is the kind of thing. Top quark. We know the top quark is there at much more than 5 sigma. We know top is produced singly instead of only in pairs at 5 sigma. We just discovered charm mixing in the D-bar meson system at 5 sigma. Okay, those are things that are 5 sigma. Okay. So single top was fairly recent. The 5 sigma was fairly recent. 3 sigma was before that, but 5 sigma took some time to get up to that. So 5 sigma is really the gold standard. And in fact, you'll hear people at LHC talk about 7 sigma. So 7 sigma is when you're really, really sure. Okay. But this is important because people will say, we can achieve 7 sigma after 10 years of running. Okay, I'm just making up a number. And then the question is whether 7 sigma is really what you want or whether 5 sigma would be okay. Okay, let's get into the searches then. So the first thing that somebody asked about were looking for something like 2 Z bosons. And how would we know that the 2 Z bosons are really coming from the Higgs? If you look at the decay, H to ZZ, and each one of these Z's decays to leptons, and you see that the 2 leptons have an invariant mass, then you have a very good idea. Here I'm using L plus L minus. In my vocabulary is that L is electron or muon. Okay, you learned yesterday to ask me that question. get it out there right before. So here L is equal to E mu. Apologies to the tau fans in the audience. Okay. I'll explain in a second why we don't use tau. So what's happening here is we have 4 leptons. So 4 leptons, each pair of which is supposed to make the Z boson mass. So the way that we do this search is we look for 2 leptons. This has to be a E plus E minus or mu plus mu minus pair. Make sure that it matches, make sure that this pair's invariant mass is close to the Z mass. Make sure that this pair, which could be a E plus E minus or mu plus mu minus, is close to the Z mass also. And then put those 2 pairs of leptons that are making 2 Z's together and see what invariant mass we find. So the thing that makes this a little bit challenging is that there's another thing that makes 4 leptons. Remember, we always have to think about the backgrounds to these production mechanisms. So how about this as a standard model background? Z to L plus, L minus, L plus, L minus. So in other words, Higgs to ZZ is not the only thing that makes ZZ. ZZ can be just produced. I'm going to not write the diagram because we'll probably make a mistake there. I mean, the Z could be radiated off QQ bar, right? So, it could be something like this, right? Okay, so I have a Q bar, here's a Z, here's another Z. Now, what's different about these compared to the Higgs? In the Higgs, you have Higgs decay directly to ZZ bar, or ZZ, sorry. Okay. So there should be an invariant mass for this Z pair that's coming from one particle, whereas these Z's will be non-resonant. They're not coming through a resonance. There should be no invariant mass peak. What you see in the plots here is you see the background, which is that standard model ZZ production. That's plotted here. You can see that it turns on about 180, but that's exactly what you would expect for this ZZ. If the Z's are produced basically back to back. Okay. If you have a 2-body decay here, so 2 incoming particles to 2 outgoing particles, the 2 outgoing particles should be basically back to back. And so that would give you an invariant mass that's most likely to be around 2 mZ, and that's what you see in the background here. The contrast is that you can see the peak for the Higgs. This actually corresponds to a Higgs at 180 degrees. You can see that this peak is not quite as easy to see as this peak would be here at MH equal 300 because it's right on the rise that you have for the ZZ production. That's one thing to notice. The other thing to notice, and we'll talk about this more tomorrow, is that this peak seems to be wider, or seems to be narrower than this peak. Right? The scale is basically the same. Is the scale the same? No, sorry, the scale is not the same. The scale here goes 140 to 240. This one goes to 200 to 400, yet this one still looks wider than this one, okay? So this one is a lot wider. We'll talk about that a little bit tomorrow. You can't see the Z. You can't see the drop-off here, right? But rest assured that if you could, it's exactly the same background that you have here. This green is the same in both cases. So I could claim that I intended to do this, to show you the turn on and show you the backside, but that's not the case. I wanted to show you the 2 signals. But you do learn the interesting lesson there from the backgrounds too. This H to ZZ is often called the golden channel. Why is that? It's very clean. It's not very often in the standard model that you get 4 leptons. The only way that you get those 4 leptons are from ZZ production itself. So very clean, and you get a very sharp Higgs peak. If you see a resonance like this, you say, aha, that is a new particle. You'd have to do some other studies to figure out if it was a standard model Higgs or not, but at least you would know that this is some new physics.
Tell me about magic, how you can make sense of this mess. How can you distinguish this from leptons? I mean, you will see thousands.
Right. The question was how we distinguish this from leptons.
How can you find this for leptons?
Right.
Identify that they came from the same molecule?
It's a very good question. So the question was, don't we have hundreds of leptons or dozens of leptons that we have to pick through? Actually not. This is actually one of the most important things to remember about hadron colliders. And I haven't hit this quite hard enough. I don't know if Matt and I hit it quite hard enough. But one of the keys for hadron colliders and this was realized for the Hadron Colliders that were built at CERN in the 70s when people were preparing these Hadron Colliders, is that you can reduce the background a lot by looking only at high PT leptons. In other words, where do leptons come in the Standard Model, if not from W's and Z's? They come from the heavy quark decays that we were talking about. So you remember us talking about the heavy quark decay where a W is part of the transition from B to C, and that W gives off a lepton. Those leptons are not high momentum leptons. They're relatively soft leptons. So the only place that you really get these high PT leptons, which after all are the weakly interacting particles, are from the weak bosons. So finding those high PT leptons was a sign in the early 1980s that the W and Z had been discovered. Just those leptons, right? Just like that. And we're using the same tricks here. So even though the cross-sections for the strong interactions for the jets are very high, you might have noticed in the cross-section plots that the cross-sections for the high PT lepton weak boson productions were 6 orders of magnitude below that. So that's what we're counting on. The probability to get one PT lepton from something other than a W and Z is small. The probability to get 2 is pretty small. So a Z is a very clean thing. The probability to get 4 is very small unless they really are coming from the 2 Z's. So that's a very good question. It's not true that there are dozens or hundreds of high PT leptons in each one of these events. There are actually very few. That's one of our key handles for all of this. So now that I mentioned that, one thing that we do have a lot of are photons in the events. Okay, so we kind of made our way from, if you look back in your notes, you'll see that this H to ZZ was very powerful in the range MH greater than 2 MZ. Okay, so I showed you what the peak looked like for Higgs mass of 300 GeV. Let's go to the opposite extreme. Let's go and see what happens for M Higgs much, much less than 2 MW. Remember, it still has to be above 114 GeV, though. So in this region, if we go back to our branching ratios again, we had a whole bunch of branching ratios for BB bar, for top, and we had one there at the bottom that was the photon, gamma gamma. Now, we'll talk about later about BB bar and tau plus, tau minus, but those end up being more challenging than the gamma gamma search, basically for reasons of the detector resolution. I already told you yesterday that measuring those jet energies that you would have from the B is hard. There's some uncertainty in the jet energies. So when I take the invariant mass of those two jets, I actually get not a very narrow peak, but a rather wide peak. And for the taus, we heard that the challenge with the taus is reconstructing them, even though they have at least 2 neutrinos and up to 4 neutrinos potentially. So a lot of missing energy in those jets. We have a way around it, but it's not quite as good as the resolution that we have on the photons. So you remember for CMS, okay? For CMS, the energy resolution was fantastic for those electromagnetic calorimeter clusters, right? You remember that for electrons and photons? Well, we're not going to look for the Higgs decaying to electrons. That didn't even show up on the branching fraction plot. But Higgs to gamma gamma did. So let's see what happens there. So if we look at just putting 2 photons together, let's find 2 high PT photons that are in the detector, and let's take the invariant mass of those 2 photons. Now, there will be a lot of background, right? There are lots of processes that produce 2 photons in the Standard Model that aren't from Higgs. Okay, that's probably this is what the 2-photon model is up there, or gamma gamma born that you see there. There are all sorts of backgrounds that are up there, but you can still see the peak for the Higgs to gamma gamma above all of that background. In fact, here's a case where having lots of background is good, because even though you may not want to calculate what the contribution is from all of these separate physics backgrounds, if you see something like this, it's a pretty good bet that over here is background, over here is background, and if it's a smooth curve, I'm supposed to have drawn a smooth curve here. Maybe it's not quite as smooth as I wanted. What you have is a background that can be fitted with some smooth function, and then these events up here are the gamma gamma, Higgs to gamma gamma events. So here's a case where having a lot of background is actually a good thing. It helps you measure the background very well. Okay. By the way, note up here that the Higgs peaks are magnified by a factor of 10. Okay. So to be real, they're actually 10 times smaller than that. This is with 1 inverse femtobarn, though, okay, which is not very much data. So if you like, just say, we'll take 10 times that amount of data, and then those peaks can be. Okay, there was a question here. No, it's true. It doesn't work like that. I shouldn't have said that.
Colored by the color of this plot.
Mhm.
Suppose like this yellow band in below.
Yes.
So it means the number is from the upper part to the end, or it just the number is just the yellow band.
Good. These are all stacked up on top of each other. So it means the yellow band has only something like 40 events per bin. Does that make sense? Okay. In other words, the contribution of the yellow band is just from here to here. Okay. So there are a total of maybe 40 events, 50 events in this bin from the yellow band, not 120. That's a good question. Okay. Okay, so these are two very clean channels. Let's talk about, we're kind of working our way down from the most golden channel to the most difficult channel. And we'll get to the end on one that's very difficult. So the next channel that I'll talk about are the Higgs to tau tau. So we're still in this low mass region here. We already talked about the gamma gamma. Let's talk about the tau tau. Tau plus, tau minus. In principle, it sounds like it should be hard because we have at least 2 neutrinos and maybe 4 neutrinos that will make our jet energies uncertain, and that will hurt our invariant mass resolution. But there's the trick that Matt mentioned, and I won't discuss too much here because I want to save it as an exercise to you. Here's a little, is there a hint? There's a hint up there. Okay. So he already gave you part of the hint, which is that you know for the most part that the tau decay products, just the visible tau decay products, are a pretty good indication of the total momentum of the tau. And you know that the missing ET in the event must be coming from those 2 to 4 neutrinos that are apportioned between the 2 taus. So the important thing that you need to do is figure out how much missing energy to assign to each one of the taus. Remember, missing energy doesn't have individual vectors that you can figure out. It just has a total. But if you can figure out that you have missing energy pointing like this to one part of the detector, maybe part of it is actually here and part of it is actually here. And those two together give you a resultant total missing energy. Let's call this E, missing energy total. Okay? So that's the key to this trick. Once you do that trick, you get a reasonably good mass peak, and that's the mass peak that you see over here in red. So the mass peak here in red is the tau, the Higgs to tau tau, and this is for one tau decaying to a lepton and the other tau decaying hadronically to either 1 or 3 hadrons. And what do you think this blue peak is here? Any guesses on what that blue peak might be? Something that produces tau plus, tau minus pairs. The Z, exactly. It's the right place for the Z, right? The Z decays to tau plus, tau minus pairs. The fact that the Z is reconstructed near 90 GeV is a good sign. Okay? So in fact, it's reconstructed a little bit low, right? It's not quite at 90, at least according to my eye here. It looks like it's more around 85 or something like that, right? I can't quite see. Or is it higher? Is it higher? It's a little bit high? Okay. Okay. Well, you'd have to calibrate where exactly that's reconstructed and see if the Higgs is reconstructed in the same way, a little bit higher, a little bit low. Okay. One other thing I want you to see here. Notice the number of inverse femtobarns needed to make this plot. Okay. So in 30 inverse femtobarns with this particular analysis for tau tau, we have how many events? I mean, these are pretty fine bins, but only 2, 4, 8 events in each bin. This is after 30 inverse femtobarns. If you go back and look at my map of the LHC, that was corresponding to basically, I can't quite remember what I wrote down, something like 4 or 5 years from now, wasn't it? Is that right? Is that what I wrote? Anyway, 30 femtobarns is a little bit of a way off. So everyone who's been asking me at the meals about when the Higgs will be discovered, you have to have patience. This is a marathon, not a sprint, okay? We have other sprints, and we'll talk about some of those tomorrow, but the standard model Higgs is not necessarily a sprint, unless it happens to be in one of these golden channels. Michael?
I can't do the arithmetic fast enough to add up the things. Are you plotting for us a 5 sigma discovery, a 3 sigma?
Gosh, that's a good question, Michael.
So 38% times 5 is...
So if we were just to be very rough, shall we be very rough here? Let's see how we would do it, in fact. Let's pretend that our analysis is just going to count the events between 100 and, 130. Shall we do that? So how many total events do we have that are from S itself? Well, actually, no, let's do the total. Let's do the total here. So total I have, boy, they don't seem to be integers, do they? I can't quite tell if they are or not. Maybe they are. Maybe they are. Let's say 5, 5, 6, 16, 20 roughly, and then here's another 5, so 25, and 27, let's say. Actually, we could make it 25 to make things easier on ourselves. Okay, 25. So what's the uncertainty on 25 if we say that it's approximately Gaussian, we're in the large number region, right? Square root of 25, okay? Right, so that's going to be our number that it could have fluctuated. Now let's count our background, good point. So count the background, what are we doing between 110, this is where we started here. So that's 3, 2, that's 5, and then a whole bunch of ones. 5, 6, 7, 8, 9, okay? So there's something like 9 background expected, 25 observed. And if you think back to what we had before with the 40 and the 10, we were taking the square root not of the 25 observed, but of the background. Okay, so the key is actually with the background could fluctuate from 9 up to 25. So a fluctuation of 9 up to 25 would be how many sigma? Anybody? So each sigma is 3, so that would be more than 5 sigma, wouldn't it? So this would be a 5 sigma discovery. I don't know if that's good enough for Michael or not, but yeah. He's very happy with 5 sigma. Okay. Okay, let's keep going then. And of course, I have to emphasize, Michael, that's very, very rough. In fact, usually if you're able to see something that is 5 sigma by eye like that counting, it's probably much more than that when it's been done properly. Okay. That's kind of my rule of thumb. So the next we have the search for WW. So the search for WW is difficult for one main reason. And the main reason is that first let's say in what regime might this be useful? So Higgs to WW would be useful in the region where we are MH basically larger than 2MW, although it's also good just below that too. So the reason that it's difficult is that here we have one W decaying to a lepton neutrino, and we have the other W decaying to lepton neutrino. So we have 2 neutrinos here and 2 leptons. This is really not enough information to give us an invariant mass peak. How is this different from the taus? The reason it's different from the taus is that for the taus we were able to make a pretty fair assumption saying all the tau products are in one mini jet. Remember Matt talking about the mini jet basically because everything's boosted because the tau has such a small mass. So everything's boosted, everything's collimated. We could assume that all the decay products are in that direction. For the W's, this is definitely not the case. So the W's are produced if it's a Higgs that's just above 2MW or not too far above 2MW. They're produced roughly at rest. The lepton and the neutrinos will go out maybe approximately back to back. So you have something like this. Here's the lepton, and here's its neutrino. Here's the other lepton, and here's its neutrino, something like this, okay? The orientations of these might change a little bit. But basically you have a large missing ET. You don't know really how to apportion it between the two W's, so you won't have a W mass peak. And in fact, you see this up here. Here's the invariant mass. You can see contributions from a few different physics backgrounds. Anybody think of how you can get 2 leptons plus missing energy? One way is you get real W's from TT bar. So just to remind you, TT bar decays to WB, and then this one decays to WB, being sloppy with my signs there, but you get the idea. Okay, so each one of those W's can decay leptonically, and in that case you would have the 2 leptons plus 2 neutrinos, just exactly the same signature, with 2 jets to be sure. But okay, so TT bar, and the other case is Drell-Yan, which would be dilepton production. So Drell-Yan has a peak that's by the Z mass. So that doesn't really contribute too much to the region where you expect the W invariant mass to be. So if you look at the invariant mass here of these candidates, it's actually pretty low. It's actually lower than you have even for the TT bar. But there's not very much, there's not a peak there for us to look at. So this is challenging. Luckily, there is one saving grace. So the saving grace is this. If we think a little bit more, what's special about Higgs to WW? Here we have a case where we have a spin 0 scalar that's decaying to 2 spin 1 bosons. Okay? And this will give us a certain spin correlation, a certain azimuthal angle or typical azimuthal angle that the 2 W bosons will follow. And the reason for this is up here. So basically the 2 W's that are coming out from the Higgs, which is spin 0, have to have opposite spin. Okay? They have to have opposite spin as they go off in these opposite directions. Whereas the W plus and the W minus, well, I guess I should say that the W plus and the W minus are coupling each one to either the right-handed or the left-handed lepton. Okay? That's what happens when you have those spins. So what you can see here is you can see the delta phi, the angle between the 2 leptons. That's basically this angle here in the transverse plane, the azimuthal angle. And you can see, I hope, although it's not quite as clear as you might hope, that there is a difference between the azimuthal angle that you see for the signal and what you see for the background. So in particular, it's supposed to be peaked lower for the signal than for the background. Okay. So these two things together, the invariant mass and the angle, are each in themselves not as powerful as an invariant mass peak. But when you combine the two together, then you can get a good amount of information. Unfortunately, they won't be quite as impressive as the peak that you would see out of those golden channels. Okay. So the question was from before, the Tevatron limit that was between 163 and 166, excluding those masses. That's because the Tevatron searched in exactly this channel, so H to WW, just above 2 MW, and found not enough candidates to be there if there were true Higgs production. So they were able to rule out Higgs production in that narrow mass range. Okay, let me finish here with the cutting edge from the past year or two. So if you go back again to the branching fraction plot, you'll see that at low mass, that is Higgs below 2 MW. Actually, I guess I have it right here. That by far the largest branching fraction would be to BB bar. And so far I haven't shown BB bar. So you might be wondering what happened to it. Where did it go? I hid it at the back because it's very challenging. Okay, why is it challenging? It's challenging because, as I mentioned, there are two reasons actually. One is that, and Matt mentioned this already, the production cross-section for direct BB bar production. Let's draw the two here. So the Higgs to BB bar production looks like this. The direct Higgs to BB bar production would look like this. I have my gluon going through my top loop to a Higgs, and then the Higgs decaying to the two fermions, which are the BB bar in this case. Okay? But this is fighting against the non-Higgs production of B bar that comes from direct gluon fusion, okay, with the S-channel gluon. You can see the differences up there between these two cross-sections. So this one, 39 microbarns, it should say, good. And Higgs, 30 picobarns. So micro to pico is a billion. And billion's a lot in physics. If it's not a lot in the budget, it's a lot in physics. Okay? Pardon me? A million. 10 to the 6th. Thanks, Matt. 10 to the 6th, a million. Good. So the other reason is this, that once, even if you were able to pick out somehow, I mean, we picked out the Higgs to gamma gamma peak above a big background of gamma-gamma events. Remember that? Why can't we do the same with BB bar? The reason is that with the gammas, it was very clean. We had a very good resolution in the electromagnetic calorimeter, whereas here we're trying to measure jets. So we're measuring the invariant mass of B bar, jet, invariant mass. And in this plot, you see exactly what the resolution is on that jet invariant mass. You can see that it has a width of about 11.5 GeV whenever we're talking about a mass of 90 GeV. This actually happens to be for Z to BB bar, but the resolution should be pretty similar for a low mass Higgs. So that's about 10%, more than 10%, actually getting close to 13%. Okay, so that means that the resolution is 13%, whereas if you do the calculation on what it was for the photons, it was tiny, right? It was. We can go back and look at the peaks again. So for the photons, it was tiny. It was few GeV. And here, it is about 4 or 5 times that. I'm going the wrong way. So this makes it hard. So that resolution is poor, and that's what makes it hard. The other problem is that the B's are everywhere. The cross-section is very high. So there are 2 ways to fix this. One way to fix it is to require leptons to be produced in conjunction with these B's. So in other words, a Higgs produced in conjunction with the W, or a Higgs produced in conjunction with the Z. That's the WH and the ZH that I have up there. So what's key about that is that then you have a high PT lepton, or 2 high PT leptons, plus the BB bar. And the background cross-section for that is reduced by a huge factor, because you can look up what the cross-section is for WB bar. And that's, again, on the order of tens of picobarns, probably, maybe hundreds of picobarns. But that's getting close to what the signal is, okay? So that helps. Another thing that helps, and Matt alluded to this, and this is the last couple slides here, is that we are able, in a certain region of phase space, to find a specific decay of Higgs to BB bar. So let me show you what we have here. So in a certain situation where the W would be produced recoiling against a Higgs at very high PT. Actually, let me just draw the Higgs like that. So there's the Higgs, there's the W. Let's say that each one of these has PT of the W, greater than 200 or 300 GeV. That's a lot. You notice that most of what we've been talking about when we select leptons and things like that are around 30, 40 GeV. So having a W with a PT of 200 to start out is a lot. What will happen? Well, the lepton and the neutrino from the W will clearly be boosted far forward, because this PT now is large compared to the mass of the W. So the lepton and the neutrino won't be nearly back-to-back anymore. They'll be boosted far forward. What happens with the Higgs? Well, remember, this Higgs is decaying, if it's a low-mass Higgs, to BB bar. So we have a Higgs going to 2 jets. If the Higgs is produced at rest, those jets will be back-to-back. But if the Higgs is being produced with a very high PT, the same PT as the W to conserve momentum, then that means that the 2 B's will be produced boosted too, so in the same direction there. Okay. This is something that happens very rarely in the standard model. Okay. So it happens rarely in the backgrounds, except for Higgs. Actually, it happens rarely in Higgs too. Here's the key. What it will look like in our detector, these 2 B's will be close together. So if I put my A to phi plot out here, again, I'll have my B jet, one B jet will be like that. The other B jet will be right next to it. In fact, these 2 B's will look like they're in the same big fat jet. Okay? So we call it a fat jet. Some people call it fat jet. Some people call it a boosted jet. And the key is to, instead of taking a large R, we were talking about this morning, you take a large R first to find that jet, to find that fat jet. That's what this picture on the right is doing, or sorry, on the left is doing. So putting both of those B's together into one fat jet. Then you try to rerun the jet algorithm with a smaller R parameter, smaller radius if you want to think about it that way. What happens then is that these two, if they're from a massive object, will break apart a little bit. Okay? In other words, they are separated enough that they can be separated into two separate jet cones. And the key here is that there's a large mass difference. I mean, these are two Bs. Each one of these B jets has a mass that should be around the B mass. But when you put the two of them together, they have a mass that's around the Higgs mass, 120 GeV. So the key signature here is dropping down from a large, large jet mass, 120 GeV, when they're put together, down to much smaller individual jet masses of 5 GeV. Okay, that is something that happens only with the Higgs. So this has been worked out. People developed an analysis with this key mass drop. Once you've identified that there was some massive object that produced this boosted jet by looking at the mass drop, then you can take the individual pieces and look at them. So the punchline is this. People actually tried this in simulation to see if it worked. And here's what happens. If you use this boosted jet technique, here they used PT of 300. So I said 200, but they used 300. They use a R for the fat jets of 0.7, and they assume a B tagging efficiency and fake rate of 70% versus 1%. So those numbers are right along the lines of what we've been talking about over the past few days. So now you could read this paper and you could say, I know exactly what Cambridge-Aachen algorithm is with R of 0.7. You're all set. I know exactly what the B tagging efficiency is. So if you make the plot now of the invariant mass, and the key is by doing this filter, you pick out the two B jets specifically. See, over on the right-hand side now, we know where the B jets are. We know what the individual B jets are, and we know they're coming from a Higgs. I should say we don't really know they're coming from a Higgs. They could be coming from a Z, like in this background here. So the blue is the Higgs. You can see it's a very good peak after all. So what helps is that we've cut down a lot of the BB bar background by requiring the lepton, and we've even further purified it by requiring this boosted jet and this big mass drop once we resolve the jet substructure. To be sure, there's still a contribution from this VV. You remember what VV is? It's either WZ or ZZ, where V is vector boson. But this is promising. So this would be another handle that we would have to try to find the Higgs at these low masses. So the summary of the whole thing is that if the Higgs is very massive, then we have access to it through the golden channel, which is Higgs to ZZ. If it's in the mid-range, then we can look for it in Higgs to WW, which the Tevatron was already successful in excluding that range. Unfortunately, excluding it would have been much nicer if they discovered it. And for the low mass, which is the region where the theory tells us the Higgs is likely to be, then we have 3 different ways, and we may have to combine these 3 different ways together to give us a signal in the end. Okay, are there any questions about this? I kind of went fast through the last little bit there. So keep your eyes open. I mean, like I said, it's a marathon, not a sprint, but the key will be testing all these techniques with the early data so we can actually look at the ZZ production and see if it matches what we expected from the simulation. And if it does, then that will be good news for us on the Higgs hunt.
What is the timeline on this?
Aha! What's the timeline? So they all have different timelines. Some of them are easier than others. It's very easy to see a peak in the golden channel because you saw the background was low. So for that, you see, I hesitate to give even any numbers. You have to look at the experiments for the numbers. For the, I think, so I will tell you this. I was just looking up what the experiments say they can do with 1 inverse femtobarn. And with 1 inverse femtobarn, which is a year's running at 7 TeV, total center of mass energy, 3.5 per beam, they said that there would be no Higgs masses excluded at 1 inverse femtobarn. Okay. So part of that is because of the 7 TeV instead of the 14 TeV. So the answer is really 30 inverse femtobarns would be the sweet spot for the Higgs searches. All these plots that I showed today with nice peaks were around 30 inverse femtobarns. So how long that takes depends on the machine. Okay, so cross your fingers. Any other questions? Michael looked puzzled. Okay.
Yeah, you stressed that for the 2-photon decays that theory, you don't really need to understand the theory all that well, or the
right? So you can see that this channel, for example, the question was, to what extent do other channels need detailed background calculations? To what extent can they be measured from smooth distributions and fit? So you could say that this could probably be fit, especially if you're not on the rising edge. If you're on the rising edge on the left-hand side, it's a little bit more difficult, so this would be okay. Actually, the only drawback here, Michael, is that the signal appears so quickly that you may not have time to, in other words, this peak here is much, much more than 5 sigma, okay? So the problem, but I think that you could do that. I think you could fit that, and you know that distribution pretty well anyway. The things that are challenging are things like this, because this depends on knowing that vector boson diffusion production mechanism, and that needs to be checked in the standard model with the Z production. Just very quickly here. So I mentioned that there was WW fusing to make a Higgs, but there's also a WWZ coupling. So this same diagram can also give you a standard model non-Higgs production that would be QQZ. Okay, actually QQ bar prime Z. Actually QQ, thanks. Let's see. What are the other ones? Higgs to WW. There is not really an easy way to fit that background. And for Higgs to BB, this is actually the one that's probably the trickiest from the theoretical point of view, I would say, for the backgrounds, because there are all these different possibilities for V plus jets in particular. There are lots of diagrams for V plus jet, and it's non-trivial, I think, to think about how you would fit that. This is, by the way, the same problem that Tevatron has with the WH search, knowing exactly what's the shape of that distribution. Okay. Well, thanks for your patience. I know we went a little bit over, and we'll talk more about the new physics searches, more generic new physics searches tomorrow.